Hello, everyone, and welcome to today's live broadcast, Contamination Control in the Hydraulic Industry, presented by Rob Fish. We are excited to bring you this educational web seminar presented by LabRoots and sponsored by Beckman Coulter Life Sciences. Beckman Coulter develops, manufactures, and markets products that simplify, automate, and innovate complex biomedical testing. More than 275,000 Beckman Coulter systems operate in both diagnostics and life sciences laboratories on 7 continents. For over 75 years, our products have been making a difference in people's lives by improving the productivity of medical professionals and scientists, supplying critical information for improving patient health, and delivering trusted solutions for research and discovery. To learn more about Beckman Coulter Life Sciences, please visit www.beckman.com. I am Judy O'Rourke of LabRoots, and I'll be your moderator for today's event. This webinar has been approved for continuing educational credits. Please click on the CE button at the bottom left corner and follow the process to receive your credits. Before we begin, I would like to remind everyone that this event is interactive, and we encourage you to participate by submitting as many questions as you want at any time you want during the presentation. Just click on the green Q&A button located in the lower left of the presentation window and type your question into the box that appears on the screen. We'll answer as many questions as we have time for at the end of the presentation. Also, please notice that you will be viewing the presentation in the slide window. To enlarge the window, just click on the screen icon located on the lower right. And finally, if you have trouble seeing or hearing the presentation, please click on the support button at the top right of the presentation window, or you can use the Q&A button to let us know that you're having a problem. Thank you. Now I'd like to introduce Rob Fish, the owner and lead instructor of BasicHydraulics.com. Rob develops and conducts training that extends the life of hydraulic components, reduces hydraulic-related downtime, and improves the productivity of hydraulic equipment. He has a wide range of experience designing and troubleshooting hydraulic circuitry. Rob earned the Fluid Power Society's Fluid Power Specialist certification in 1987. His circuit design work has been featured in Hydraulics and Pneumatics magazine. Rob's education, training, and hands-on experience allow him to provide hydraulic-related training that is interesting, understandable, relevant, and useful. Please join me in welcoming Rob Fish. I will now turn the presentation over to him.
Hello, everyone, and thank you for attending. I've been teaching basic hydraulic classes for a long time now, and every time I teach a class, I'm reminded of a story that Zig Ziglar taught once at a seminar I attended. He said that every year, millions and millions of people go over to their hardware store and buy something they don't want. They buy a drill, and they really don't want drills. What they want are holes. They just have to buy the drill in order to be able to get the holes. And I think that when it comes to a contamination control webinar, we're talking about the same sort of thing. What we're here for is not so much contamination control as the benefits that we get from contamination control. Years ago, I taught a basic hydraulics class for a company in Decatur, Illinois. And during the class, they mentioned that they were having some problems with their servo valves. That one servo valve was breaking down about every 6 to 8 weeks, and they couldn't find a reliable repair shop. So instead of repairing them, they'd come into the habit of replacing their servo valves. They were averaging about 7 breakdowns a year, and it was costing them, between the cost of servo valves and downtime, over $36,000 a year. Now, as we'll talk about a little bit later on, all hydraulic components are sensitive to contamination. And in fact, the #1 cause of hydraulic component failure is contamination. And servo valves are more sensitive to contamination than many other types of hydraulic components. In fact, if contamination was an allergy suffered by hydraulic components, servo valves would be suffering from that severe peanut allergy. They are extremely sensitive to contamination. After the class, the people in the class convinced their company to spend a bit over $3,000 to control the contamination reaching the servo valve. Now, I haven't talked to these folks in quite a while, but the last time I talked with them, they'd gone 3 years without the servo valve failing. For that 3-year period, that worked out to be a saving of $105,000. So they invested $3 grand and they saved over $105,000. They controlled the contamination, but the result was a huge cost savings. During today's webinar, we're going to do a basic non-technical look at what contamination does to hydraulics. The idea is that we want to extend the component life, we want to reduce downtime. The bottom line from extending the component life and reducing the downtime is that we are going to have companies save money, increase their profits, and hopefully save some jobs because they're profitable and can afford to employ more people. In the next 40 minutes or so, we're going to go over what hydraulics is, how hydraulics work. We'll talk some about particle sizes. We'll go over some of the basics of contamination. There's a rule of thumb for filtration that we used to use years ago in the good old days. We'll talk about that and what current accepted practices are for contamination. And also we'll talk a little bit about how clean is clean enough and how you achieve that level. We'll finish up with a few minutes of question and answers, and then we're out of there. To start with, just to make sure that I understand how much to go off script, can we do a quick poll now, Don? I'd like to have the poll put up. And please, let me know how familiar you are with hydraulics. Okay. Thank you very much. So let's start with talking a little bit about what hydraulics is. Textbook definition of it might be a way to transmit power by pushing on a confined fluid. And I'll use a log splitter to explain how this works. We're going to start with a power. Power is going to come in from the gasoline engine. And with hydraulics, we're going to transmit that power over to a log and use the power to split the log. When we turn on the gasoline engine, the shaft of the gasoline engine is going to start to rotate. As the engine shaft turns, that in turn is going to turn the shaft on the pump. We're transmitting the power from the gasoline engine to the pump. As the pump turns, hydraulic fluid is pushed from the reservoir into the pump, and then the pump is going to push the fluid up to a control valve. That control valve controls the direction of the cylinder that we're operating, so we're going to call it a directional control valve. And that directional control valve has got 3 positions. In one position, the fluid goes into the directional control valve, turns around, goes out that blue line at the bottom, goes back to a filter, which is going to hopefully take out some of the contamination, through the filter and back into tank. The fluid is making a loop from the reservoir to the pump to the valve, through the filter, and back to tank. Now we're going to go ahead and remove the log from the drawing just so that you can see the cylinder a little bit better. And I'm going to shift the valve. I'm going to shove that handle forward towards the cylinder, and parts inside that directional control valve are going to shift. Instantaneously, we're going to have fluid go from the directional control valve into the back end of the cylinder. Some people call that the base end or the cap end. We'll call it the back end for now. As fluid enters the back end of the cylinder, it's going to push the cylinder rod out. And as the cylinder rod comes out, any fluid that happens to be in the rod end is going to go out the rod end port, shown there in blue now, and go back to the directional control valve. And from the directional control valve, it's going to head back through the return line, through the filter, and back out to tank. If we shift the valve again into the center position, fluid once again goes from the pump to the directional control valve, through the return line filter, and back to tank. We shift the valve again and pull the handle back, and now the pressurized fluid is going to go into the rod end. And as the fluid goes into the rod end, the cylinder is going to retract. As the cylinder retracts, any fluid that happens to be in the back end of the cylinder is going to go through the directional control valve, through the return line, back to the filter, and finally back to tank. Now, if you had X-ray vision, which some people think would probably be a pretty nice thing to have, you would see that when the cylinder is retracted, the oil level in the reservoir is up near the top. And when the cylinder extends, the oil level in the reservoir drops down to the bottom. We'll take a look at how a hydraulic cylinder works to see why that happens. Now, I see that there are some people attending today who have no experience with hydraulics, so let me simplify this. A hydraulic cylinder is much like those old push-up pops that we used to have. With a push-up pop, if you push on the stick, the ice cream comes out the top. If you turn the push-up pop over and you push on the ice cream, then the stick is going to move out. And that's the exact same thing that happens with a hydraulic cylinder. When we push on the bottom, the stick comes out. So if we compare the two, a cylinder and a push-up pop have a lot in common. The cylinder's got a tube on the cylinder, the push-up pop has a tube, and on the cylinder we call it a body. There's a little platform on the push-up pop that holds the ice cream. In the cylinder, we'll call that the piston. The stick on the push-up pop is pretty much the same as the piston on a hydraulic cylinder. So if we put the whole thing together and turn on our X-ray vision, we can see that we've got the body containing the piston and the rod. Things would get a little bit messy if we just threw oil against the bottom of the cylinder. So we're going to put on end caps. We'll put an end cap on the bottom and an end cap on the top with a couple of ports, and then we'll connect some plumbing. Turning on our X-ray vision again, you can see the piston inside and the rod inside. And now if we put fluid into the bottom end of the cylinder, that fluid is going to enter the cylinder and it's going to push against the piston. As the fluid pushes against the piston is going to move forward, and any fluid that's on the rod side of the cylinder is going to get pushed out of the rod end port and go back to our directional control valve, and as this happens, our cylinder extends. When the cylinder is extended completely, as the cylinder extends, any fluid in the piston end is going to go out and is going to go to the valve. When our cylinder has completely extended, we can push fluid into the top end port, the rod end port, and that fluid will push on the piston and cause the cylinder to retract. And as the cylinder retracts, any fluid on the piston end is going to go back through the directional control valve and back to tank as the cylinder retracts. When the cylinder is completely extended, there's nothing in the bottom end of the cylinder. So the fluid can completely fill that area, and in this particular case, it'll hold about 3 gallons of oil. When the cylinder retracts, the rod takes up some of the space. And with that rod occupying some of the space, we can't put as much oil in the rod end as we can and put in the other end. It's got a pretty good sized rod, and this particular cylinder will hold about 2 gallons of oil on the rod end. It means if we put 2 gallons into the rod end, 3 gallons are going to get pushed out. And if we put 3 gallons of fluid into the back end, then 2 gallons are going to come out of the piston end, and that's going to change the fluid level. Now, somewhere out there, someone is probably thinking, what the heck does this have to do with contamination control? If we go back to our log splitter, we'll see that on the top of the reservoir, there's a little breather, and that allows air to go in and out of the reservoir as the cylinder extends and retracts. When the fluid level rises, fluid is pushed out of the breather and goes out into the nearby atmosphere. When the fluid level drops, the space that is created by the fluid level dropping, we have air from the nearby area go push in through the breather and fill up that space. Now, as the air is coming in through the reservoir, any airborne contamination in the area has the opportunity to come in and go into the reservoir. We end up with the possibility of having contamination inside the reservoir. Now, if you look around most machines, you really don't see any contamination floating in the air. But back in 2008, Hydraulics and Pneumatics published an article that says essentially, we don't want any particles larger than 10 microns inside our hydraulic fluid. We measure contamination in hydraulics in microns. Remember that servo valve that I mentioned before? they were having servo valves fail until they put on a 3-micron filter in the pilot line. So when we eliminated the 3-micron particles, the servo valve continued to work. So we've got hydraulics and pneumatics saying for most hydraulic systems, nothing bigger than 10 microns. For servo valves, nothing bigger than 3 microns. And unfortunately, the breather used on many hydraulic systems has a 40-micron filter. That means that that element that is filtering the air going in and out of our reservoir can let particles as big as 40 micron enter the reservoir. And the breathers have got a little bypass built into them so that if the breather element gets clogged, instead of filtering the air, all of the air goes in, so particles bigger than 40 micron can enter the reservoir. I don't know about you, but when I first started working with hydraulics, I had absolutely no clue what 40 micron, 10 micron, and 3 micron particles were. So let me give you some sizes for perspective. If you pretend that that purple dot is a grain of salt, it would be about 100 micron. That little backwards U on the end of the 100s is the abbreviation for micron. I don't have many of them left, but when I had them, my hair was about 70 micron in diameter. Young folks can see things as small as 40 microns. Those of us a little bit older need cheaters to see things that small. A white blood cell is approximately 25 micron in diameter. Let me repeat that. A white blood cell is approximately 25 micron in diameter. It means that hydraulics and pneumatics and everybody else is saying that we don't want things in our oil as large as a white blood cell. Do not try this, please. However, if you were to cut yourself and bleed into the hydraulic reservoir, your white blood cells are big enough to void the warranty on most hydraulic pumps, motors, and valves. And if it was a piece of metal the size of a white blood cell, it could cause the hydraulic components to fail. Red blood cells are 8 micron. So 8 micron is kind of okay to go floating through hydraulic fluid, but it's too big to go through the servo valve. And when we talk about the number of components, if you were to try using your blood as a hydraulic fluid, there are so many white blood cells and so many red blood cells inside our blood that there are too many pieces of contamination to run through a hydraulic component. So why do we care about airborne contamination? It's because as the cylinder extends and the fluid level drops, any air contamination in the air that happens to go through the breather is going to go down into the reservoir and mix in with the fluid. As our pump runs, hydraulic fluid is going to be drawn into the pump. Any contamination that's in the fluid is going to run through the pump, possibly damaging the pump. That fluid is going to come out of the pump and go into our directional control valve, once again, possibly damaging the directional control valve. Then go out of the directional control valve into the cylinder. And as the cylinder extends, any fluid in the rod end of the cylinder is going to go back in through the directional control valve. And then our fluid containing contamination is going to go through the return line and get to the filter. Unfortunately, filters are not 100% effective at removing contamination. Return line filters, they might be 80 or 90% efficient. Cheap return line filters might only be 50 or 60% efficient. And when a filter gets dirty, it'll go into bypass mode. And when the filter is in bypass mode, all of the dirty fluid goes through the filter and the filter is 0% efficient. So we can count on at least some contamination going through the filter, going through the return line and back into tank. And then as the hydraulic system continues to run, it can go through the pump again. So contamination in a hydraulic system might cycle through the system many times before being trapped by the filter. Now, if you would, please do me a favor, hover your hand just a wee bit over your desk or the table beside you. Don't touch it, just a wee bit over the desk. Now move your hand back and forth left to right. And you're not touching the desk and there's absolutely no friction. And thanks, you can stop doing that. That is how many hydraulic components operate. The moving parts inside, pumps, motors, and valves, they don't actually touch each other. There's a thin film of hydraulic fluid that separates the different components. So as parts inside our different components move, that hydraulic film that's there provides a thin layer of lubrication. It provides a seal to keep things from moving out. It moves heat away from the moving parts, and it carries contamination away. Now, don't do this, but if you were to put your hand over your desk and pour some oil down, you could now put your hand on the desk and rub it back and forth, and your hand would be separated from the desk by that thin layer of oil. And ideally, we would suggest that your hand would move a little bit easier than it would if there was no oil there. Now, if we used a really thick oil, we could put some contamination there. In this case, let's say we put a piece of sandpaper down. If we put that oil on top of the sandpaper, you could rub your hand back and forth over the sandpaper, and it wouldn't do much damage. It would still do some damage. It just wouldn't do a heck of a lot. So if we have good quality lubrication, we can handle a little bit of contamination. Now do me a favor and put your hand back on your desk. And this time, press down as hard as you can, just with your hand. And as you're pressing down, you're probably straining a little bit. And how hard do you think you're pressing down? Thanks very much. Appreciate that. When I press down, I can generate about 30 pounds of force. So pressing down, we generate somewhere around 30 pounds of force. If you're stronger than me, you might make 40. If you're a little bit less bulky than me, you might make 20. And when I put my hand in contact with the desk, the area that's touching the desk has an area of about 15 square inches. So if I do a little bit of math, I've got 30 pounds of force that I'm pressing down with, and I'm dividing that over 15 square inches. That comes out to about 2 psi. I've got 2 pounds per square inch that I'm pushing down with, and I'm generating about 30 pounds of force. And my guess is that you're probably going to generate about the same amount. Let's go back to the log splitter. That log splitter can generate over 1,600 psi and 20,000 pounds of force. Other hydraulic equipment, like the press that the servo valve is on, can generate over 5,000 psi. Going back to the log splitter, that 1,600 psi is 800 times as much pressure as we generated while pushing on the desk. And the question that I've got is, can you imagine what would happen if you had a piece of contamination on your hand that was pressed with 1,600 psi? Now, when we look at basic hydraulics, we're going to say that pressure in a confined fluid acts equally in all directions. Pascal's law, and anytime you take a basic hydraulics class, we're going to teach you that. If we pretend that this device you're looking at is a hydraulic component, it's got a pipe coming in from the left and a pipe going out to the right. We're going to put flow in from the left, and we're going to have flow go out to the right. Now, let's put a little piece of contamination going into the piping. As look at that, turn the pipe sideways, you can see that the contamination is completely surrounded by the fluid. So that means that because the fluid is all the way around the particle, that 1,600 psi is not slamming the particle against the piping. It's just kind of carrying it along, and we've got the same pressure on all sides. In most hydraulic components, we've got a passageway, and then we've got a very narrow opening and maybe a small orifice. The narrow openings in the orifice can allow for lubrication, they can meter the flow, they can provide a drain path, and do all kinds of things that are vital to the operation of a hydraulic circuit. Going back to our piece of contamination, we can see that it's entering the pipe. And as you've probably guessed, it's going to tumble and it's going to turn, and it reaches that orifice, it's going to block it completely. Now, with the orifice being blocked by the contamination, there's no way that any flow can get through the orifice. And if we're operating at low pressure, maybe 100 psi, 200 psi, 500 psi, that pressure is just going to hold the particle there, and it's not going to do much damage. And at low pressures, if we reverse the flow or we turn off our system, that contamination might just drop down to the port, drop down inside, and then maybe next time we start up, it'll get carried through the orifice without doing any damage. But if we're operating at high pressure, when that little piece of contamination hits that orifice, it's like when we were talking about pushing that piece of contamination into your hand at 1600 psi. That contamination is going to get driven into the orifice. It's going to block the orifice. It may damage the orifice. And when we turn off the system, it's not going to break out. We're going to have total catastrophic failure of the component, and it's going to need to be repaired or replaced. Now, in addition to catastrophic failure, there's two other kinds of damage that can be caused by contamination. If we've got a bunch of small particles moving over and against things, it can act like sandpaper and erode the internal parts. Pretend for a moment that this is the stationary part of a hydraulic component, and we're really going to magnify it a lot. We're going to put a moving part above and a thin film of hydraulic fluid. Now, that thin film of hydraulic fluid is actually only microns in height. It's smaller than a red blood cell. And because this is a contamination webinar, we're going to put some contamination in it. And as the contamination moves through there, it's going to gradually wear the parts, kind of like if we were running sandpaper through there. And as it wears the parts, the opening between the parts is going to increase. And that larger space is going to allow more hydraulic fluid to flow between the parts. So if the part used to leak 10 cubic inches a minute before, it might now leak 15 or 20 cubic inches more because there's a bigger space for the fluid to go through. So why does this matter if we get more leakage? Well, the speed of a hydraulic motor and hydraulic cylinder is determined by the amount of fluid that flows through them. Going back to our log splitter, let's say that our pump is putting out 10 gallons per minute, which we abbreviate as GPM, and it takes 10 seconds for the cylinder to extend. If we reduce the amount of flow to, say, 5 gallons per minute, cutting the flow in half is going to double the amount of time that it takes. So instead of taking 10 seconds to extend, it's going to take 20 seconds to extend. So as internal parts wear, our equipment's going to run slower. In addition, as we leak internally, we're going to generate heat. And when we heat up fluid, it gets thinner. And when it gets thinner, it doesn't do as good a job of lubricating and protecting as thick fluid does. And as a result, the thinner fluid is going to increase the chance of our components being damaged by contaminations. The other type of issue caused by particles is something I could call scratch and dent, or more accurately, scratch and chip. Once again, we've got a very, very greatly magnified piece of hydraulic componentry. We're going to have fluid come in from the bottom. It's going to go through the component, and it's going to go out to the right. We've got some very, very small areas between the moving parts that are filled with a thin film of hydraulic fluid that'll carry away the heat and provide some protection from contamination. We aren't going to get any flow through that because it's so dogma. Actually, that's not correct. We're going to get cubic inches a minute of flow going through because they're so narrow. Now, the sizes of these openings, as I said, are greatly exaggerated, and all the parts are separated by a thin film of fluid. Now, if we move a part to the right, we're going to block off the port, and now flow comes up to that movable part, and then it stops. And if we move it back the other way, then we get flow through there. Now we start to move again, and this time a chunk of contamination is going to get trapped between the movable part and the stationary part. In this case, the term chunk is totally subjective. The chunk might be a metal particle 20 micron long, 12 micron high, and 8 micron wide, just picking numbers out of the air. But it's smaller than a white blood cell. Moving part's going to shear that chunk and make it break into a whole bunch of smaller parts. It's also going to chip off the edges of the moving part and the stationary part. In addition, it's going to scratch where it goes through the moving part. And what happens with all of that is we create more contamination and we create a pathway for fluid to leak by. So now, instead of sealing completely when we close the valve or close whatever it is, we end up having some leakage going through. Where before we might have had 60 gallons per minute going out to our system, now maybe a gallon or two is going to leak and go back to internal leakage and not be able to use for our system. And what does this matter? Well, let me tell you about Joe's Woes. Picture there you see is Sam. He's the owner of Continental Construction Contractors. Actually, that's not true. This is clip art, and that's not really his name. I've changed the names, and you'll see why here in a moment. A few years back, Sam bought a new excavator and some trucks to use on a job that he'd won. And with what he charged for his hourly rate, he made $40 an hour profit on each and every one of those trucks as they operated for a job that he did for 60 days. In the course of the 60 days, he ended up making over $76,000 in profit. He determined during that job that his excavator averaged filling his dump trucks 3 times an hour. Now, Sam's company had been busy, and they haven't done a really good job of maintaining their equipment. Back when everything was new, his pumps put 60 gallons per minute into his system. Contamination caused by stuff coming in and contamination coming in through the breather cap, contamination that was ingested as the system operated, it wore the pump down, and now instead of putting out 60 gallons per minute, he gets only 51 gallons per minute of usable fluid to do the work. The excavator has slowed down, but the change happens so slowly that nobody really noticed it. Now, last August, Sam's company won a bid for virtually an identical job to the one they did 4 years ago. And because it was so close, Sam sharpened his pencil and decided that he would cut his costs a little bit, cut his prices a little bit, and he based his bid on doing the exact same work that he did 4 years ago. Unfortunately, because the excavator was operating slower, it took 69 minutes to fill 3 dump tracks instead of 60 minutes. That extra 9 minutes cut into his profits, and the bottom line is that instead of making $76,000 like he did for the first job, he made only $23,000. A loss of, I did the math wrong, that's something like $50,000. So he didn't make anywhere near as much money as he thought he was going to make because of the contamination slowing down his machine. And now we come to Joe's Woes. This is Joe. Joe was the excavator operator. And when they didn't make as much money on this job as they made before, Sam fired him because he thought Joe was doing a terrible job. And Joe wasn't doing a terrible job. It's just that the contamination caused the pump to slow down, which caused the excavator to slow down, and he just couldn't work the machine as quickly as possible. Bottom line, contamination is the #1 cause of hydraulic component failure. Most damage done to components is done by particles way too small to see. So where does it come from? Some of the contamination gets built into the machine. The person making the machine, he's cutting the pipes for the log splitter, and he cleaned them out by blowing compressed air through them. Looked through the pipes, didn't see any contamination, said, oops, this is clean. Once again, contamination that can damage components can be as small as a white blood cell. The person welding the reservoir did the same sort of thing as the pipe fitter. He did the welding, he looked inside there, no contamination. Someone may have used a grinding wheel near the log splitter when it was being assembled. Some contamination comes in when the machines operate. Every time the cylinder extends and retracts, you have the possibility of debris falling on the cylinder and getting pulled back into the system. A big one is that new hydraulic fluid is not clean enough to use in a hydraulic system. It needs to be cleaned before it can be used. And if fluid is poured into the reservoir instead of being pumped in through a dedicated port, opening the port to pour it in can ingest contamination into the system. During maintenance, if you open up any ports, that's an open invitation for contamination that we can't see to enter the system. And I know that it doesn't happen with anybody here, but there are places where maintenance people don't use plastic plugs, caps, and on ports and fittings. In the old days, we just used to say that our rule of thumb was to use a 10-micron filter on pumps and motors and a 3-micron filter on servo valves. I'd like to introduce you to my friend Tim. This is the way Tim looked 5 years ago. He's running for his high school track. And that year, 5 years ago, his Aunt Alice mailed him a size medium sweater for Christmas. A beautiful thing. And Aunt Alice has been mailing Tim a medium-sized Christmas sweater every year since. Now, when Tim got to college, he started working out, and this is Tim today. Tim's changed, but Aunt Alice is still sending him that medium-sized sweater. It doesn't fit anymore. Like Tim, hydraulics have changed. The rule of thumb in the old days might still work in some cases, but hydraulic components are now made to tighter tolerances, smaller clearances, and they operate at higher pressures. In the old days, a piece of contamination that would go through a component without causing much damage now gouges, scrapes, and breaks as the fluid goes through the tighter clearances. So when you want to figure out how clean your fluid needs to be, ideally you would consult the manufacturer's literature and determine what they require for the level of contamination cleanliness and set a target based on the manufacturer's recommendation. The International Standards Organizations created a chart that helps us describe how much contamination there is in fluid. A lot of different people use it to specify cleanliness levels for warranty, cleanliness levels of what your fluid is when you have it tested. And the chart looks something like this. We're going to measure the number of particles in a milliliter with a piece of testing device. And a milliliter is the equivalent of about a quarter of a teaspoon of fluid, or if you've got an eyedropper, about 20 drops from an eyedropper. And we're going to chart 3 different sizes of particles. We're going to keep track of how many particles we have that are larger than 4 micron but smaller than 6 micron. We're going to keep track of how many particles are larger than 6 micron and smaller than 14 micron. And we're going to keep track of how many particles are larger than 14 micron. So we might look at a number like ISO 141210. And that describes a fluid. The 14 says that we've got between 80 and 160 particles larger than 4 micron and smaller than 6. The 12 in the 1412 tells us how many particles we have between 6 and 14 micron. And the 10 tells us how many particles we have bigger than 14 micron. And well, ideally you'd go to manufacturers and you say, how clean does it need to be? There are some standards that are generally accepted. For systems with servo valves, we're looking at using a minimum of 16, 14, 11, which means that we have 320 to 640 particles in the 4 micron size, 80 to 100 in the 6 to 14 size, and 10 to 20. That's not a lot of particles. And once again, we can't see any of these particles. They're all smaller than a white blood cell. For general hydraulic systems, we might look at the chart and say that we want a 17, 15, 12. And we can tell how many of each size we have just by looking at the chart. New hydraulic fluid is often rated at ISO 191714. If you remember, we said that high pressure and servos needed to be filtered to 16, 14, 11, Normal operation is a 17, 15, 12, and the bottom line is that new oil is not clean enough to use in your hydraulic system. And we talked about blood a while back ago. Blood has more than 4,000 white blood cells per milliliter and 5 million red blood cells per milliliter. If our hydraulic fluid had as many particles as our blood does, it would destroy every single hydraulic component out there. So the question is, how do you determine if your hydraulic fluid is dirty? I don't know about you, but me, I struggle to maintain my weight, and I've got what I call fat pants. And if I don't pay attention to my weight, I gradually creep up until the only thing I'm comfortable in is my fat pants, and it generally takes, 15 or 20 pounds to get there. So if the only way that I knew that I was getting overweight was when my fat pants were the only comfortable pants, I'd be fat before I got into them. So what I do instead is every morning I get on a scale and I check out what my weight is. Now, the fat pants method of checking whether your oil is dirty or not is to look at your components. And if your components are failing, if your equipment is running slowly, if your equipment doesn't work properly when it gets hot, that means that you have got contamination and you need to do something about it. But by the time that happens, the damage has been done. The hydraulic equivalent of me stepping on a scale each morning is to take a fluid sample, measure the contamination, and find out what the reading is on the ISO contamination chart. If you're fortunate enough to have a particle counter, you can test in-house, but there are a bunch of labs that will test your fluid and provide results at a reasonable place. Regardless of where the testing happens, it's got to happen. Now, I take a prescription medicine every single day. My doctor requires I come in for a visit and a blood test every 6 months. When I get into the doctor's office, a nurse has me step on the scale, she takes my pulse, she measures my blood, they draw my blood pressure, and then they put all of that information, well, they used to put it in a folder on the door so the doctor could look at it before he came in, but now they put it on a computer, but the same thing happens. We sit down and we go over the results, comparing what's happening now with what happened before. And the whole idea is that we're checking to see if anything has changed so that we can correct it before it gets too much of a problem. And you should do fluid tests on a regular basis for the exact same reason. You want to catch the problems while they're still easy to fix. The goals of this webinar included extending hydraulic component life and reducing downtime. As you've probably guessed, the biggest factor in meeting those goals is to set a good ISO cleanliness level and maintain it. Other things that you can do in order to make your components last longer is keep the operating temperatures within the range of your components. If the fluid's too hot, it doesn't do a good job of protecting your system. Maintain proper additive levels in your hydraulic systems, avoid pressure spikes and excessive system pressure, keep the water out of your petroleum-based fluids. We're getting close to the end here. We'll go through a few more suggestions on ways to reach your ISO level cleanliness. Set a target level, either by consulting the manufacturer's literature or using one of the suggested ISO levels that we talked about earlier in the webinar. You need to figure out where you are. So start off by testing your hydraulic fluid to determine how contaminated it is. And if it doesn't meet the standards that you set, you need to clean it up and or replace it. When you're going to put fluid into a system, any new fluid should be filtered several times before it goes into the system. If I was king of hydraulics, you would take a drum full of hydraulic fluid and you would run it through a filter cart and put it into an empty drum. And then you would clean the source drum, and then you would run the fluid through the filter buggy again, putting it back into the empty drum, and you'd repeat that 2 more times. And yeah, I know, that's a royal pain in the patoot. But you know, I went out to buy a bicycle helmet, and when I went and looked at the bicycle helmets, some of them were awfully doggone expensive. And I said to the salesman, do I really need to buy one of these expensive bike helmets? And as you probably guessed, what he said to me is, how much is your head worth? If your hydraulic downtime is expensive, if your hydraulic components are expensive, you need to take the time and filter the fluid before you put it into the system. And if I was king of hydraulics, the only way that you could get oil into a system would be to pump it in with a filter cart through a dedicated port. It would take oil through the filter cart and it would go in through a dedicated port. You might also consider installing a kidney loop system where you have a dedicated filter that draws fluid out of the reservoir, it filters it, and then it returns it to the reservoir. So those are two things that you can do without any problem at all. These next steps, consult a fluid power specialist or an engineer before making the changes, because if they're done correctly, they can really help. But if you do them wrong, they can cause catastrophic failure, destroy the components, and when you tell people, Rob Fish told me to do this, it makes me look bad. Okay? First thing would be to add high-quality pressure filtration to your system. Second would be to upgrade your return line filter to a much higher quality, finer Micron filter. And the third thing would be to replace any 40 micron reservoir breathers with 3 micron units. Once again, don't do any of those changes without consulting an engineer, because if you do them wrong, it can cause some severe problems. Come back to how much can you save by doing all of this. That company in Decatur, Illinois, saved $105,000 in 3 years. Sam's Excavating Company lost $53,000 in just 3 months because they've gone several years without filtering the fluid. The amount that you save is going to depend on your exact circumstances, but generally, without a doubt, any money that you spend on contamination control pays for itself in the long run. And with that, I think that we're pretty much covered all the information that we needed to cover in the webinar. So I believe we're ready for questions.
Thank you, Rob, for that informative presentation. It is time for Q&A, so if you have a question you'd like to ask Rob Fish, please do so now. Just click on the green Q&A button at the lower left of the presentation window, type your question into the box that appears on your screen, and click on the send button. We'll answer as many of your questions as we have time for. And I believe I see some questions coming in, so just give us a moment here. An audience member asks, which kind of fluid is used and what are the properties?
The fluid that's being used in hydraulics, we can have a petroleum-based fluid and we can have a synthetic-based fluid. When we talk about contamination levels, most of what I've talked about today is pretty simply used on petroleum-based fluids. The same principles apply with synthetic fluids. It's just that the filtration requirements are slightly different because of the way that the synthetic fluids are designed.
Okay, and while we're waiting for more questions to come in, I would like to once again thank Rob Fish for his presentation and ask if you have any final comments. Rob, do you have any final comments you'd like to share with the audience today, or are you?
No.
Okay.
No, I think that we've covered everything. The only thing that I would suggest is when you're starting a business, they say that the key to success is location, location, location. And as you've probably guessed, my feeling is that when it comes to making money with hydraulics or having hydraulics be a cost-effective way to do things, the key is filtration, filtration, filtration.
Well, thank you for that. And we have another question for you. How likely is it for the hydraulic components to leak fluid out of the hydraulic circuit and contaminate the environment?
With a well-designed system, the chances are very, very slight. When you get a system that you operate with high pressure spikes, where you don't maintain it properly, then some of the hoses and fittings can start to leak, in which case you can get leakage. But generally, with a well-designed system that's operated within its normal operating parameters, the chances are very, very slight that you'll have any fluid leaking out.
Okay, well, thank you for that, and I'll continue to wrap up, but any people who have additional questions, of course, we'll take them. I would like to thank our sponsor, Beckman Coulter Life Sciences, for making today's educational webcast possible. This webinar has been approved for continuing educational credits. Please click on the CE button at the bottom left corner and follow the process to receive your credits. And before we go, I want to let everyone know that today's webcast will be available for on-demand viewing through August 28, 2017. You'll receive an email from LabRoots letting you know when the webcast will be available for replay. Please share that announcement with your colleagues who may have missed today's live event. That is all for now. Thank you for joining us. We hope to see you again soon. Bye.